Question 2 reads, a crate of mass 2 kg is pulled to the right across a rough horizontal surface by a constant force F, right? Rough horizontal surface, right? Rough horizontal surface tells us there's some friction involved. It's not just a smooth surface, right? There's some friction involved, right? And then it says the force F is applied at an angle of 20 degrees to the horizontal as shown in the diagram below, right? We can see force F there. And then 2.1.1 says draw a labeled free body diagram showing all the forces acting on the crate, right? So on the crate, since it's on a surface, there are some forces that are obvious, right? I could say obvious forces that are there, right? Naturally, because it's on a surface, right? So let's use a lighter color. Let's use yellow, right? So we have our dot here, so representing that it is a free body diagram, right? Let's just make a dot like that. And then we know weight, right, is always acting downwards, vertically downwards, right? So that can be our weight. And of course, this is on a surface, right? So it's also experiencing a normal force. It's also experiencing a force from the surface as well, right? So that force is the normal force. So let's just call it N, right? Or Fn if you like. And since this is on a rough horizontal surface and we know that our object is moving to the right, as they've indicated to us there, right? It means our frictional force is acting opposite the motion, right? So our frictional force is going to be to the left. So we can just call it Fk, which is the kinetic friction because this object is moving. Or you can just call it F or Ff, right? So representing the frictional force, right? And of course, we have a force applied here, right? So this is a specific force applied, but it's applied at an angle of 20 degrees, right? So it's not going to be straight like this, right? It's like this, right? Or alternatively, since that is a diagonal force, it means, right, it has a vertical component and some horizontal components, right? So you could have drawn it like this. We have our weight, we have our friction here, which you say it's Fk, we have our normal force, right? We have our normal force, right? Let's just say Fn. And then of course, since there's a diagonal force, you can represent it in its two components, right? So we have a component, right, which is vertical, right? So let's use a lighter color, right? A vertical component, right? So we can just call that Fay, which is the force applied, right? Which is the vertical component of it. And we also have here we have what Fax, right? So we could have also drawn it alternatively like that, right? Or you could have just drawn it at an angle, right? Of course, this is 20 degrees here, right? And then, yeah, let's move to the next question, which asks us to calculate the magnitude of the normal force acting on the crate, right? But before that, they've given us some extra information here, right? So it says a constant frictional force of 3 newtons acts between the surface and the crate, right? So we've already predicted that there will be some friction involved because they've told us here that it's a rough horizontal surface, right? So now it's telling us about frictional force, right? It says a constant frictional force of 3 newtons acts between the surface and the crate, right? And the coefficient of kinetic friction between the crate and the surface is 0.2, right? So we have the frictional force and the coefficient of friction. I don't know why they are giving us the coefficient of friction. Let's find out. So it says calculate the magnitude of the normal force acting on the crate. Normal force acting on the crate, right? So we know that the normal force is the force that the surface exerts on the object, right? And in this case, we have some information here with the frictional force and the coefficient of friction. So we can basically use this formula here. Let's write 2.1.2. It asks for the normal force acting on the crate. So we know that our frictional force formula is Fk is equals to coefficient of kinetic friction, right? Multiplied by what? The normal force, right? So we're looking for the normal force and we've been given the frictional force. We've been given the what? Coefficient of friction. So let us replace, right? So our frictional force, they said it's 3, and our kinetic friction, we got it as 0.2, right? 0.2 multiplied by what? The normal force. So we're looking for the normal force, right? And to find the normal force alone means we need to remove whatever is disrupting it. On the right hand side of the equal sign, we have 0.2, which is multiplying with the normal force. In order to get rid of the 0.2, we divide both sides by 0.2, divide 3 by 0.2 as well. What we do on the left, we do on the right, And then we get our N, which is our normal force, is equals to 15 newtons, right? So we got that. Let's move to the next question. They ask for 2.1.3, they ask us to calculate the magnitude of force F. So let's just zoom into this diagram and just delve deeper into what is actually going on over here, right? Just pink. And then we understand that this force is diagonal, right? And we understand that if something is diagonal, if a force is acting diagonally, it means it has horizontal components and some vertical components within that force, right? So here we know that it's at an angle of 20 degrees. So if you just form a right angle triangle like this, we have our 90-degree there. So in this case, the force applied, the F, right, which is what we want to call, which is what we want, right, is diagonal, which is the hypotenuse in this case, right? And of course, this is what we could just call this Fx, and then this is what Fy, right? So what we are looking for is this F. But in this triangle, the only thing that we have here is the angle. So we need at least one side, right? At least the vertical component of this, which is Fy or Fx, right? In order to calculate F, right? So we cannot just use the angle on its own to calculate the hypotenuse, right? So in this case, we understand that this object is moving horizontally, right? It's not making any upward movement or downward movement. So if it's not making any upward movement or downward movement, we can therefore conclude that the forces acting upwards is equal to the forces acting downwards, right? So let's equate that, right? So what this means in a nutshell, it means that in this case, if we look at the way if we've drawn the diagram like this, right? The free body diagram like this, it means we separated the diagonal force into its vertical and horizontal component, right? So in this case, it shows better, right? The forces that are acting up and the forces that are acting down. So we've agreed that the forces acting up is equal to the forces acting down. So we can see that the only forces that are acting up, it's Fay, which is the vertical component of the force applied, and the normal force, which is the force that the surface exerts on the object going upwards, is equal to the weight, which is the only force acting down. So in a nutshell, we're just saying that F, let me use a lighter color, let's use white, right? So we're just saying Fay, we can just call this Fay, force applied, right, which is the vertical component of it, plus Fn, which is the normal force, has to be equals to the weight, because we said that the forces acting upwards is equal to the forces acting downward, because this object is not making any upward or downward movement, right? So if maybe you think, maybe initially we may think that since this guy is pulling, right, this thing at an angle of 20 degrees, right, it is actually the force that he's pulling. It's like, let's say I have an object, right, that has a less height than I am, right, that is lower than I am, and I'm actually tall, and then I'm pulling an object with a string, right? Obviously the string will make an inclination, right? The string will have an angle to it, right? But that does not necessarily mean that the box, right, or the object that I'm pulling will be traveling diagonally, right? It will be traveling along the surface, as here they also indicated it's travels horizontally, travels across a rough horizontal surface, right? So here, right, so let's continue here, right? So our Fay is what we're looking for. Our frictional, our normal force, we have it, right? We've calculated it in the previous question, and our weight, we can calculate it, right? So let us add that to the step of what we're doing, right? So let's start by calculating, right? 2.1.3, right? So let's start by calculating the weight, which is the force acting down, which you want to equate to the two forces that are acting upwards, right? So our weight is equals to mg, right? Our m is the mass of the object, which is 2, in this case 2 kg. It's always in kilograms, multiplied by 9.8, right? So our weight is 19.6 newtons, right? And so we have the weight and we have our frictional force. So we're looking for Fay, right? So let's just replace into that formula, that little formula that we've made ourselves. So Fay, right, plus Fn, which is a normal force, is equals to weight, right? So the force is acting up is equal to the force that is acting down, right? So our Fay plus our Fn, we got it as 15, is equals to 19.6, which is the weight, right? So our Fay is obviously equal to this 15. When we take it to the other side, we're going to subtract it. It's going to be 19.6 minus 15. We get 4.6 newtons, right? So that is our vertical component, right, of this F that we're looking for, right? So we've gotten the vertical component of it. So we got this as 4,6, right? So let's just redraw this triangle roughly here. We've got a triangle here. We've got an angle of 20 degrees here. We have F here and we have 4,6 here, right? So now we have enough information in order to calculate F, which is our hypotenuse, right? So now we have an angle and a sine that is opposite this angle, and we are looking for the hypotenuse. So the ratio that comes to my mind is sine, right? Sine of 20 degrees, right? So let's write sine of 20 degrees is equals to, our opposite is what? 4,6. Our hypotenuse is the F that we're looking for, right? So if we make F substitute to the formula, we're going to get 4,6 all over sine 20 degrees, right? And as we type that on our calculator, we're going to get 13,45 newtons, right? So we've done that. Let's move to the next question, which says, which asks for us to calculate the magnitude of the acceleration of the crate, right? So let's look at this acceleration of the crate. So acceleration, right, is moving in the axis, or let me just say is moving in the axis of the movement of the object. What I mean is that acceleration is moving, it's moving parallel to the surface, right? So acceleration is moving parallel to the surface. So acceleration is not moving at an angle because this object was pulled at an angle, right? But it's moving with the object, and we've been told that the object is moving horizontally. So it means our acceleration is horizontal. So if we're trying to find acceleration, we need to consider only the forces that are horizontal, right? So here, the forces that are horizontal, let's go back to our free body diagram here, right? So the forces that are horizontal here are Fk, right, which is our frictional force, which you've been given as 3 newtons, and the other one is Fay, right, which is the horizontal component of that F, which we've just calculated in the previous question, right? So if you can get this, and we have this, right, so let's just find Fay here, right? So because those are the only forces that we'll consider, because acceleration is moving horizontal, right? So I believe it's 2.1.4 if I'm not mistaken. So we know that Fay, I mean Fax, right? Because this is so Fax is equals to F. We use cos to find the horizontal component of the force. We use cos, right? Our angle is 20 degrees, right? So our force is 13,45 multiplied by cos 20 degrees. And we get an answer of 12.64 newtons, right? But we can't, we prefer not to round it off because this is not our final answer, right? So let's just keep it to 4 decimal places, right? So it's going to be 12,6389, right? Newtons, right? So now we have the forces that are acting horizontally, right? Which is what acceleration is about in this case, right? So here we have Fk and F this, right? So we know from our formula, Newton's second law, right, that F net is equals to ma, right? So we're looking for acceleration, so that's why we're using this formula, and we understand that acceleration, whenever there's acceleration involved, we use Newton's second law, because Newton's first law says the object will continue in its state of rest or uniform motion unless acted upon by an unequal force. So when an unequal force acts upon it, that's when acceleration is involved, right? So here we have an acceleration of the object, so we need to calculate it. So F net, so we're considering the forces that are acting horizontally, and we said that we have friction, and friction is obviously acting opposite the motion of the object, right? So let's start with the motion of the object. We said that its horizontal component is what? 12,6389, and minus, because it's acting in the opposite direction, our friction that we've given us as the 3 newtons, right, is equal to ma. Our m, right, our mass of the object is 2, and we're looking for acceleration, right? So we're looking for acceleration alone, and the only thing that is disrupting us from getting acceleration alone is this 2 that is multiplying with acceleration. So to remove something that is multiplying, we divide, right? So let's divide both sides by 2, divide this side by 2 as well, and then we get our acceleration as meters per second squared, right? So here we can round off our answer to 2 decimal places because this is our final answer here, right? So which is the acceleration which we've just calculated, right? So let's go to the next question, right? 2.2, right? It says a massive rock from outer space is moving towards the Earth. State Newton's law of universal gravitation in red. So we can state that it's on the examination guideline or the textbook, right? And 2.2.2 says, how does the magnitude of the gravitational force exerted by the Earth on the rock change as the distance between the rock and the Earth becomes smaller? So if the distance between two objects becomes smaller, it means they are getting closer and closer to each other, right? So what we understand by gravitational force, right, is if we can write the formula here, F is equals to G m1 m2 all over r squared, right? So the square is the square of the distance between the centers, right? So what we understand, right, is that force and the distance, the square of the distance between their centers, is inversely proportional, right? So it's like this, right? So force and the distance is inversely proportional. So what they're asking, right, is that if this distance becomes smaller, what will happen to the force? So because of its inversely proportional relationship, right, it means that if the other one becomes smaller, the other one will increase. So our answer here, we can, as they say, we choose from increases, decreases, or remains the same. So here we can conclude by saying 2.2.2 that it will increase, right? The reason it will increase is because the gravitational force is inversely proportional to the square of the distance between their centers, right? So this part of reasoning is also found in the definition, right? So the gravitational force is inversely proportional to the square of the distance between their centers, right? So please forgive my handwriting, it's not that good looking. And yeah, so we are done with this question. So if you have any questions, you may ask. Sure, I hope you understand.